This one down here would generate a high frequency. Okay. Remember that later on when we start talking about filters, with this one down here, the high frequency object, we normally have to average, so we use a low pass filter to kind of blend these together so that they don't look so grainy. And then up here we use what they call a high pass filter. That makes the edges of the object stand out, it sharpens the image. Okay. But on the PLES down here, okay, this one also has to be rotated 90 degrees. So you take one in the X orientation and one in the Y orientation. The last one that's down here, I don't know if you can really see it that clearly, but this is a piece of lead that has holes in it, or a piece of plastic that has holes in it. And basically you take one picture with this, and this gives you your uniformity, your linearity, and your spatial resolution all in one picture. Okay, this is called the orthogonal hole phantom. I don't know very many people that use this though. I had an orthogonal hole phantom, and it used to take forever to do a picture. Okay, but your linearity and spatial resolution tests are supposed to be done weekly. Okay, so at the conclusion of your uniformity tests, then you should also have one of those types of images. Okay, I wanted to go back to our picture over here. Okay, so head looks pretty good here. Okay, we've got our spectrum. We have our peaks. Now, one of the things that I did notice over here, peak in at 124.8 keV. Uniformity 6.28%. What they're measuring here is what we call the differential uniformity, which means it looks at the pixel that has the highest number of counts, it looks at the pixel that has the lowest number of counts, and then it divides that by the average. So in other words, the highest minus the lowest divided by the average multiplied by 100% will tell you what your average is. Remember we said that you cannot have more than a 10% uniformity difference. Okay? And so what it did basically, it was comparing these two images here. Or this is the one where it used to calculate the how many pixels were off. Then over here, this is what it looks like after the correction. Okay. Now over here though, okay, these corrected images. Remember we said the limit is 10%, and this thing is rapidly approaching that 10% correction. Okay? This is the differential, this is what they call the integral correction here. Remember, differential looks at the entire gamma camera face, integral looks at the ones in the center field of view. But some of the things that are, the correction is pretty great, uniformity, and it's approaching the problem areas, but notice the resolution. Are you guys happy with that resolution?
No.
That's terrible. The technologist should probably have this thing looked at. There's usually two problems that cause this. Either your camera is going bad, or the phantom that you're using is beyond the resolution of your camera. In other words, you can buy these 4-quadrant phantoms with different size LED strips, and if the LED strips are too small for them to be seen by your gamma camera, then this is what you're going to get. That's especially true of older systems. So if you have one that has very tiny LED lines in there, it's not going to be seen by an older system. The other problem is true. One of the questions that somebody had put on a board exam once was the technologist, or a doctor complained to the technologist that the images of the patients were getting worse. So the technologist pulled out his, bar phantom tests and showed them to the doctor, and they were fine. They showed no change. What was the problem? what do you think the problem might be if you have a situation where the diagnostic images are getting worse, but the bar phantom images look the same?
Doctor's going blind.
Doctor's going blind? Yeah, possibility. No, actually what the solution to that problem is that the person bought a phantom that the lead strips were way beyond. I mean, they're just too big. So it would take a long time before those big lead strips are going to look bad. In the meantime, the subtle changes were affecting the diagnostic images. So when you guys buy a gamma camera, they will normally tell you what the resolution is. Okay? So you buy a phantom where it matches that resolution. If you buy something where the lead bars are too big, you're really not testing your system. You're just, it's going to be a long time before those big lead bars are going to look horrible on the picture. Does that make sense? Sort of? I'm trying to think of a good analogy.
So you want a bar phantom where the lines are minimally together?
Well, you want to have, now in this case here, the bars are too small, and they're way below the resolution of the camera, so you're not going to see them. I mean, I don't even see those big lead strips, which I should see. Okay, so this one has the opposite problem in that the resolution looks terrible because I don't see any lead bars, more or less. But the other problem would be is if I bought ones that had great big lead bars, and if there were any changes, I wouldn't be able to see them. I mean, it'd be a long time before you'd be able to see those changes. Okay, so that was gamma head number 2. Let's take a look over here. Okay, here's our peak. So, you guys like that peak? Mr. Singh, do you like that peak? Well, what is it? So the doctor's going to come to you and say, Mr. Singh, I don't know that much about nuclear medicine. Can you tell me is there a problem with our gamma camera today? What are you going to tell him? Ashley, what are you going to tell him?
Nothing's wrong with it.
Okay, what's wrong with it?
Well, the small peak right there, I think that's way too high. It's supposed to be way lower. And it has a double peak, so something's not right with the way that the camera was set. You may have it on the wrong isotope, or something's wrong. And I don't like how on the lead bars, how it was off-center by a lot.
Yeah, and again, let me warn you about when you guys do something, anytime you're assigned a task, the effort that you put into that task is measured and graded by your supervisor. So if you turn in something that looks like that, you're probably, like you say, it's off-center, and you notice that this peak here looks pretty good actually, right? And it's telling us that it's 124 over here. So what should that peak have actually been?
122.
Okay, it should have been 122. Okay. So let's take a look over here. Whoa. 142. And you said that we're seeing 2 peaks. So here's the 142, then what would this one be?
122.
122. So what does that tell you?
Yeah,
There's technetium contamination.
got it set wrong.
Okay, well actually what happened is there's technetium contamination. Okay? You've got 2 peaks from 2 different radionuclides. We should be looking at the 122 peak. Your gamma camera is going to automatically adjust its peak to whatever the height or whatever the energy of the radionuclide is that it detects. In this case here, it detected technetium. Okay? So probably this little dot here might be some technetium contamination on the camera, on the collimator. It's not on the uniformity source, because it would have been detected over here, but it's definitely detecting it over here, and so that's, that was a good observation. Okay?
I have a question.
Yeah.
What if you had like a point source that was in the background within, when you didn't have it shielded at all, would the gamma camera pick it up, especially if it was intrinsic like that?
Yeah. In fact, what some technologists do before they put the collimator on, if they're going to do an extrinsic flood, while the collimator is off, they'll do an acquisition just to see if there's any contamination in the room being picked up by the gamma camera. And what's good about that is that that is a very sensitive radiation detector, plus it's going to give you a spectrum that tells you what you're dealing with. Okay? So if you're thinking about it once in a while, you might just want to, when the detector head is off, just do a couple of minute acquisition and see if there's any room contamination, because it'll pick it up very nicely and tell you what it is. But see, the problem here was that the technologist didn't pick it up. This was actually one that was done at one of our clinical affiliates, and it was done by a graduate from the other school. Okay? I mean, unfortunately, as I said, people get complacent. Oh yeah, I did the flood, I did the uniformity and the corrected and uncorrected, and I did the bar phantom, but they don't know what the heck they're looking at. You know, they do it and then they just start scanning patients after that. Okay? And then over here, okay, again, the correction, very close to 10%. Whenever you have a lot of scatter radiation, now would this scatter radiation from the 122 be picked up in the 140 window?
Yeah, it's lower.
Yeah. Well, remember that with a 20% window, I should be picking up 126 to 154. But this peak here, I would probably be picking up a couple of additive type of, I would be picking up some of this. Okay? And anytime you have a situation like that, it's going to degrade the image. So that was a very good observation. Okay? Then we do uniformity. Oh, lordy, lordy, lordy. What do you think here?
Blood field was off when it was
Okay, again, this boils down to what type of a flood. This is a flood phantom. Now remember, a flood phantom, what's the difference between a flood phantom and a flood source?
One's tech and one's cobalt.
Okay? The tech you have to prepare every day. You have to inject technetium into a water-filled phantom and then shake it. And okay, this is an air bubble.
Would that be an air bubble?
That was an air bubble. Very good. Okay? And so they took 3 pictures of it with different intensities. This is a real good picture of the, remember what's this over here?
Edge pack.
Edge packing. Yeah. Okay? So they took 3 pictures without solving the problem. Okay, here we go. Daily quality flood. 2 heads.
F2.
What do you see? Anything?
F2.
Sector 2 is all screwed up.
Okay, so you're all noticing this area over here, correct?
Yeah.
Yeah,
Okay.
there's that spot on detector 1. I don't know if that's something on the film or if that's something.
Oh, on a paper.
Yeah. Well, you see this? Yeah. What if we would have had something like this?
Contamination?
Destroyed colony.
There. Say, oh my goodness, what's that there? Okay, we got something there. But this is the actual problem here. But this is exactly what you would have to do to diagnose something like this. Is the screens get dirty? People put their fingers on screens. Do people? I don't know where the source of this problem is. It might be up here. In this case, it's here. Okay, so we got rid of the problem. But do you understand in real life, if I would have seen that, I would have said, uh-oh, there's something there that's we got to take a look at. That would have been a hot spot, wouldn't it? Probably. Okay, that's a burned out PM tube on the edge. Okay? Okay. Now, once in a while, what we do is some off-peak images. Okay, this is with the cobalt setting. This is with technetium. And then this one here is xenon. Okay? What we're trying to do is, you can see the pattern of the, can you guys see the PM tubes there? Okay, sometimes they get out of adjustment. And when you guys have what they call an annual PM, or preventative maintenance thing, then what they do is they'll individually tune each of the PM tubes. So the ones that are all white here are good. The ones that are black, those are the ones that are out of tune. We look over here at this image here, and this image here, and it shows you the ones that are probably needing some correction. What they do is they adjust the voltage. And what part of the PM2 voltage would they be adjusting? Or to what power, or to what specific component of the PM tube would they be adjusting the voltage? Okay, the diodes. Yeah, what they'll do is they'll turn the voltage, like in this case here, they would turn the voltage up, and here they would turn the voltage down. Okay? So that the thing is uniform. These things down here, these are what they call profile slices. And basically what they do is they create a region of interest that includes the entire crystal. It's like this here. Okay? When I do a profile slice, I can either look at it this way, or I can look at it diagonally, or I can look at it on the x-axis. And it just shows me the number of counts. So here I'm just looking at a single row. This is probably line 32. I don't remember. So this is 0, this is 32, and then over here is 64, because this is a 64 by 64 matrix. If I would have turned the orientation of this object running the opposite direction here, then I would have done the profile slice. But I can increase the size of the profile slice. So in other words, I can expand this thing so it includes the whole crystal, and then I want to see if there's any real obvious areas of non-uniformity. Does that make sense? So by looking at this thing here, this is giving me a graphical representation of what the uniformity should be. And if it's truly uniform, this should just be a straight line. But if you have any areas that are not uniform, you'll either see a dip or you'll see a peak. Okay? So that's what you're looking for with that. And on this one here, okay, so we have one that, these two off-peak images look really crappy. The one where it has the corrected images looks a little bit better. So what you're seeing, okay, this one here is this graphical representation here. This one here is this graphical representation here. So in other words, you can look at that and say, okay, there's something wrong. Just, because looking at this visually, your eyes, how much difference in density do we need to have in order for us to see that there's a difference with this? Does anybody know? A little bit higher than that. Okay, about 25%. Okay, your eyes actually visualize things logarithmically. So over here, there's actually only about 16 different colors. We have white and we have black, and then there's like 14 shades of gray in between. Really, that's about as many as your eyes can see. Okay, it's nice to have all of those hundreds of thousands of colors that we can use, but the fact is that your eyes can only see about 16 different shades of gray between black and white. Okay, so that's one thing that they'll do sometimes. if they need to check your PM tubes to see if they need to be balanced or to be adjusted. Okay, here's another example of that here.
What is that called?
It's just basically, it's a uniformity test where they're just creating a profile. You can see the difference on here. Here's the uncorrected and here's the corrected. So there's the uncorrected over here and here's the corrected over here. You see the difference? The Gamma camera has noticed the areas that need to be changed. So in this picture here, this is your one picture that you need to have to show that you don't have any major problems. Because what will happen, if I had a burned out PM tube or something on this image, on the corrected image, the computer would fill it in. So if all you ever did was corrected pictures, you're not going to see any problems with your camera.
That 25% density difference, is that for black and whites? Or?
Yeah, that's for black and whites. For color, you know, on a Gamma camera, I mean not on a Gamma camera, but like for color displays, I'm not really sure how many different shades of colors you can see, but when you guys buy a Gamma camera or when you buy a computer, you can have a tremendous number of shades of colors that you can display. What I'm trying to find here, I wanted to show you why that could be a problem. Okay, here's the flow study. Kidney study. Oh, you think so? Okay, here's the static one here. Yeah. That's a problem, isn't it? You have a cold spot or a photopenic area on the study, and so we don't know, is that a problem with the liver or is that a problem with the patient? Okay. So, and then the funny thing was, now this is a three-phase scan. I think the patient, they were looking for like osteomyelitis in the spine or something. I don't remember. It was over at UCLA. But the problem was that this should have been caught on the daily uniformity, which obviously it wasn't. So now we have a new situation that has to be resolved. Either this patient has to be re-injected. One of the things that I also noticed was there's like a defect in this kidney over here. You guys see that little defect in the kidney? Okay. So I don't know if that's something, that just might be a cyst or something, I don't know. They weren't working the patient up for that, but what did occur was this. So we have our cold spot up here, and then down here we have, and I don't know if that's something in the bone or if that's a ureter. You know, there's definitely something here. Okay, so what should we do for this?
Oblique.
Okay, oblique or lateral?
Respect.
Respect. Yeah. I would probably say in this one here that a lateral would, well, I don't know, because both of these anatomical structures are posterior. So you might actually have to do posterior obliques to get the best picture. Okay, so in this case here, probably an RPO, and see. I'd probably do an RPO and an LPO, and actually, is this posterior oblique or anterior? Is this an anterior or posterior image? Okay, it's a posterior image. So I would probably get both obliques, and then I would get, what lateral would you get?
Left lateral.
Okay, left lateral, and then you do spect. Okay? So that's good that you're able to look at something like that and see that there's something going on. Okay? Now, okay, another type of a test that you may do, there's another phantom out there called a Rollo phantom. You probably won't see this done very often, but sometimes in order to get an idea of the contrast of your imaging system, so in other words, like how many colors does it display, and is it accurately displaying those colors? Okay, so if you notice we have 1, 2, 3, 4 by 1, 2, 3, 4. So we actually have a phantom in here that's designed to represent a 25% change between the number of counts it collects. So in other words, there would be 100 counts here, there would be 75 here, 50 here, 20, so in other words, they have different numbers of counts in here to represent the different shades of gray and colors that you would have on your film. Does that make sense? Remember I told you you basically only see 16 shades, so on CT scanners, MRI scanners, and our nuclear medicine, we typically only display 16 colors. So that's what this thing is checking. This thing isn't a requirement. Most physicists would probably do this on your system, but this is something that I think it's a pretty good little test. Okay. One of my students was playing around. I told him, here they moved the point source very close, so they were trying to see if it would create a distortion artifact. Here they have, they call a gap collimator, so they use for cardiac imaging. And then, I don't know what they were doing here. I think these are just, But you understand that when you're trying to represent changes on your patients, this is one of the things you need to check. Okay. And then going back to our, this is the one that I love the most, okay? This is my favorite phantom, or my favorite images, okay? And so this again talked about our statistical analysis. When we acquire an image, if we're using a 64 by 64 matrix, that means that there's about 4,096 pixels, right? And if you figure, what was the minimum number of counts that we try to get in each one?
49.
Well, I mean, how many counts do you want in each pixel, roughly?
50,000.
How many?
50,000?
No. Remember, we want to have at least a 5% error. So for two standard deviations, for two standard deviations, that's 40,000 counts for 1%. So for for a 5% error, you'd have 40,000 divided by 25, which is what?
1,600.
About 1,600? Okay. So over here, this tells you the average number of counts per pixel. So that far exceeds our 5% error that we're looking for. So that's good. Okay, this tells us the total number of counts that were acquired. So this is 33,554,171. On your daily floods, you need to make sure that you achieve that 5% error for two standard deviations. So you need to look on the average number of counts and determine that you've acquired that many. So in other words, if you come in late and say, oh my God, I've got 50 patients waiting for me, I'm just going to do a 100,000 count flood and then I'm going to get started. That's not the correct way to do it. You need to acquire that 3 million or however many million counts in order to make sure that you meet that standard or that statistical thing here. And then over here, remember the real standard deviation and the Poisson? Okay, what was the difference between those?
Poisson is a single measurement.
Okay. Well, remember the real standard deviation, this is Poisson. So that means your computer took the counts that were in each of these 4,096 pixels, subtracted the average, calculated the difference, squared the difference, and then calculated the variance on it, took the square root of the variance, and that's where the real standard deviation came from. So how long do you think it would take you guys to go through 4,096 pixels, calculate the difference and square it, and go through the statistic? I mean, it took you a good, what, 5 minutes for one sample? Okay, so multiply that times 4,096, and you can see why we like to have a computer available to do our statistical analysis. And again, remember what I told you before is, okay, so if I look at the square root of 2360 is 48, right? Okay, so this Poisson standard deviation is basically the square root of the average up here. Okay, the real standard deviation is that really horrible calculation with 4,096 pixels. Why am I interested in comparing the two? Okay, if I have a really good system, these things shouldn't be that different. Okay, this is telling me that my sample is far away from the real population. Okay, so it's telling me that I have a problem. There's a problem somewhere. These should be a lot closer. Okay, and then remember we have the integral differentiation. Let's see, Mr. Viet, what is the integral differentiation? Okay. Andy?
It's the entire image.
It's the entire image. What about the entire image?
Differential between like the darkest and the lightest spots in the entire image.
Okay. What we're looking at is the range, remember? So I find the pixel that has the highest number of counts and the pixel that has the lowest number of counts, and I subtract it. Okay? So that's the integral. Then what's the differential, Cynthia?
It's the difference of the... Your went blank. Your picture went blank.
Oh, I'm sorry. Oh, not too far the other way. You shouldn't make this where you can rest your hand on it. Okay, so back to my question. What is the differential then? Okay, now remember this is the integral uniformity, this is the differential uniformity. Huh?
The differential is only over the center field of view, the uniformity in the center.
Okay. It's only in the center. Okay, so
The differential, the whole count.
the integral. The integral, I could have a hot spot here and a cold spot here, anywhere in the useful field of view. Okay, and they don't have to be adjacent to each other. Okay, remember the differential. Okay, first of all, it's only going to involve the central field of view. And that always is 80% of the useful field of view. Okay? But in addition to only looking at the center of your crystal, it looks at pixels that are adjacent to each other. So it will look at pixels that are like usually in groups of 5. 1, 2, 3, 4, 5. Okay. So it looks at pixels that are in the same row, and it looks at pixels that are in the same column. And usually you'll look at them in groups of 5. So 1, 2, 3, 4, 5. So basically, you know, this is a little bit more sensitive way of determining if there's non-uniformity or if there's uniformity problems. Okay? Does that make sense? So, in this particular thing here, because we're going to be starting to talk a little bit about spec quality control here now. Okay. So that's what those two are there, is the integral and differential. Sometimes they'll put the ratio, and the ratio is going to be the difference between the real and the Poisson distribution. But I bring that up because you're going to have a doctor at some point in your career who asks you, what do these numbers mean? Okay. Do you think in medical school they study this? No. And if they're a radiologist, they'd probably never see this. It's highly unlikely that they would ever even deal with this situation. Okay? So that's why you have to deal with it, because you need to know if your equipment is operating properly. Don't ever get complacent. Okay? Always look at your numbers every day, as stupid or as boring as it may seem. And then over here, now this was the uncorrected image. Remember that if you have the ability to correct and uncorrected images, you need to take a picture of both. Okay? So again, over here we have the same thing. Now the only difference with this one down here is that it tells you how much correction occurred. So you see all these defects that are in the first picture. Okay? When it's corrected, notice it says it's 10% correction. So that means we're right at the limit of having to have somebody come in there and tune this thing up or fix it for us. Okay? But you notice the differences now. The difference between the real and the Poisson distribution, 70 versus 48. Okay? It's a lot better, isn't it? The ratio is down to 1.5 roughly. The differences in the integral and the differential are much lower. But again, what this 10% down here is telling you is the gamma camera is artificially adding counts to fill in those areas. What the gamma camera will typically do is, or the uniformity computer will typically do, is it will either add counts to fill this in, these gaps, or it will subtract counts from the outside and make the other ones lighter. The way that you can tell is by measuring how much time it takes to acquire the flood. Both of these are about 3 million counts. So if I do a 3 million count flood with the uniformity correction off, and it takes 60 seconds, and then I do another picture for 3 million counts with the correction on, and it takes 30 seconds, that means that my correction is adding 50% of the counts. So by measuring the time, or by actually measuring the number of counts after a certain period, you can calculate what the percent correction is. Does that make sense? Okay. And again, that's important to know, because if it's more than 10%, then you better have somebody come out and take a look at your camera, or you better do a PM on it. Okay? Now, some of the other tests that we have, on the handout here, the resolution of a system, and what I want you to do is draw a square root, draw a radical sign for that. Okay? But the thing that we're basically looking at here is spatial resolution is done with your linearity test. Remember that linearity is only to make sure that your lines are straight. Okay? And it says it's the ability of the gamma camera to accurately determine the original location of the gamma ray in the X and Y plane without the collimator. Maybe also expresses the ability to accurately reproduce small differences in radionuclide concentrations in closely spaced areas. So in other words, how close can two objects be to each other and still be seen as separate objects?
So
So spatial resolution is the same thing as the bars?
Yeah. Well, when you do the resolution images, or when you do your bar phantom, you're also doing resolution. So when you look at the picture, ideally you would like to see the smallest number of bars that are there. Okay? Rarely does that happen. But if you only see the large bars, then that means you probably ought to buy another Phantom, or you better find out why your Gamma camera has such bad resolution. Okay? Typically, I would say that our Gamma camera should have a resolution of at least 1 centimeter, or around 1 centimeter roughly. But, okay, so the number of different ways that we do this. Okay, resolution value is expressed as full width at half max, or full width at 10th max. Okay, let's talk about what that means. We have energy resolution,